a model that fits in your pocket but remembers 100 million tokens. This week, a developer named NodeMind dropped a new model called Shadow 250M Instruct, and the specs are aggressively lean. This is a 250 million parameter model trained from scratch on 30 billion tokens of English text, followed by roughly 700 million tokens of instruction tuning. The deployment package, including the vocabulary, is just 60 megabytes. It runs at about 400 tokens per SE-cond on a standard laptop CPU and consumes only 80 megabytes of RAM. The base model was trained on 30 billion tokens of FineWeb, and the README notes that the vocabulary is not a standard embedding table. Every token is a fixed 512-bit code, taking up 8.4 megabytes for all 131,000 tokens with 0 trained parameters. The developer tested this custom vocabulary on the WordZim 353 benchmark, achieving a Spearman correlation of 0.619 compared to 0.029 for random codes. The real engineering feat here is the long context mechanism. The model keeps the most recent 2048 tokens in standard FP16 format, acting like a normal key value cache. Everything older gets compressed to 1 bit and written directly to your hard disk. The compression ratio is roughly 320 bytes per token. This means you can store 1 million tokens of history in roughly 320 megabytes of disk space. The model was trained from the very first step to retrieve from this disk cache, supporting up to 100 million tokens of history. However, the README clarifies a crucial limitation due to a limited budget. It was not trained to reason over those tokens. It finds facts and reads them back, but it does not think across them. Let's look at the language modeling quality. The developer measured the base model on held-out English web text that was never seen during training, specifically educational web pages with 2048 token windows. The results are a cross-entropy of 3.15 nats per token, a perplexity of 23.3, and a compression rate of 0.99 bits per byte. To put this in perspective, the README compares Shadow against official releases of well-known small models. A GPT-2 model with 124 million parameters sits at 548 megabytes. A SMOLM to 135 million parameter model is 269 megabytes. Even a QLNI 2.5 half billion parameter model is nearly 1 gigabyte. Shadow is 60 megabytes, and none of those larger models read 100 million token archive from disk. The developer provided reproducible samples to show what this actually does. When asked to explain photosynthesis in 2 sentences using greedy decoding, the model gives a standard correct definition. When asked for a poem about the sea with a temperature of 0.25, the output is coherent but slightly repetitive. The most impressive test involves the archive. When asked for the serial number of a device called GRUS-189, which sits 50.6 million tokens deep in the archive, the model retrieves the correct serial number, SN442976. The developer notes that because it is a small model, you should expect mistakes on open facts. And it is not claiming to beat larger models, in general, reasoning. The community reaction on the machine learning subreddit was focused on scalability. One commenter asked if this would work on larger models. The developer responded that nothing in the method is tied to the 250 million parameter size. The ternary feed-forward network plus 1-bit projections should carry over. They provided a scaling ratio based on the 60 megabytes per 250 million parameters baseline. A 1 billion parameter model would land around 240 megabytes. A 3 billion parameter model around 700 megabytes, and a 7 billion parameter model would be roughly 1.7 gigabytes. Another commenter expressed amazement that 2-bit and 1-bit compression could yield these results. How did they find this sweet spot? The developer explained that they ran many experiments trying different weights like 0.125 bits, 0.25 bits, 1 bit, and 1.5 bits. They trained a small float model first and used it as a reference point to find the optimal compression. This iterative process allowed them to identify the specific quantization levels that maintain the retrieval capabilities while keeping the model small. The project was named after the developer's first dog, Shadow, marking it as their first big independent project. The takeaway here is that extreme compression does not strictly require massive parameter counts if you change how the model accesses memory. By moving long context to disk and keeping the model itself tiny, you get a system that runs on almost any hardware. The full kit with a demo and before and after numbers is included in the repository. The code is in the QLNI Shadow 250M Instruct repository, and the weights are on Hugging Face under NodeMind Shadow 250M. This is NeuralNoisex. If you want to run a model that remembers 100 million tokens on a laptop that fits in your pocket, check the links below. See you next week.